Good morning, everyone. I'm Suhani, and today I'm going to be talking about the construction and working principle of a DC machine. So, my roll number is 24011A0569, and my faculty for this subject is G. Raju sir. So, today we will talk about the following topics. First, we'll look at what a DC machine is, then, we'll look at its construction, and then we'll look at its equivalent circuit, and then we'll look at the working of the two types of DC machines, which is, of course, the DC motor and the DC generator. So let's go ahead and start. So, a DC machine is basically an electromechanical device which converts direct current into mechanical energy or vice versa. So, there are two types of DC machines. First is the DC generator and the DC motor. So, the DC generator converts mechanical energy into electrical energy, and the DC motor does the opposite, which is converting electrical energy into mechanical energy. So the DC generator is based on the principle that when a conductor is rotated in a constant unidirectional field, a voltage will be induced in it. So we can say that it is based on Fleming's left hand rule. Okay, no, sorry, right hand rule. And the DC motor is based on the principle that when a current carrying conductor is placed in a magnetic field, a mechanical force will be exerted on it. Or, in other words, we can say it's based on Fleming's left hand rule. So, now coming to the construction of a DC machine. So, there are a lot of components of a DC machine, like the armature, the yoke, the magnetic the magnetic system, and the field windings and the commutator. So we'll look at each of them one by one. So first, the yoke. The yoke is the outer frame of the DC machine. It basically protects all the components of the machine. So it's usually made up of materials which have high permeability and high mechanical strength. So like silicon steel, for instance. But in practice, it's usually made up of cast iron or cast steel. So it basically serves the following purposes. First, it protects the internal machine parts like the armature, the windings, the poles against mechanical damages. So basically from the environment. So it houses the magnetic field system, and it provides a low reluctance path to the working magnetic flux. So, and also it supports the rotor or armature through bearings. So now coming to the armature, it is the moving part of the DC machine. So it's basically a system of conductors or coils that can rotate freely on the supporting bearings. So basically the working torque and the EMF both are developed in coils of the armature. So it consists of two main parts, namely the core, the armature core, and the armature winding. So the armature winding is formed by interconnecting the armature conductor. So whenever an armature winding is turned with the help of a prime mover, then voltage as well as magnetic flux gets induced within it. So this winding is allied to an external circuit, and it's usually made up of conducting materials like copper. So next, coming to the armature core. So as we know, the rotating part of the DC machine is called the armature. So the core consists of a shaft upon which a laminated cylinder called armature core is mounted. So the armature core has grooves or slots on its outer surface. Um, so the laminations are insulated from each other, but they are tightly clamped together, so they are crowded together. So in small machines, the laminations may be keyed directly to the shaft, but in large machines, they are usually mounted on a special frame. So, but like you would ask, like why do they laminate the core? So the reason for that is to reduce current by to reduce eddy current losses. So what's eddy current? So eddy current is basically the concentric currents which flow due to the presence of magnetic field inside a conductor. So to basically protect against that, we laminate the core of the armature. So insulated conductors, usually copper, are placed in the slots of the armature core and are fastened around the core to prevent them from flying under centrifugal forces when the armature rotates. So now coming to the commutator. So what is a commutator? So it's basically a mechanical rectifier. It's a cylindrical shaped device and it's also made up of copper. So the outer periphery of the commutator has slots to carry commutator segments. So the commutator is mounted upon the DC machine on one side of the armature, and the armature conductors are connected to the commutator segments with the help of copper lugs. So basically, the commutator performs the following two functions. So first, it collects the current from the armature conductor in a DC generator. So, but in a motor, it supplies the current to the armature conductor. So it's opposite. So, and also it converts the alternating current of the armature into unidirectional current in the external circuit with the help of brushes and vice versa. So it converts alternating to direct current and vice versa. Now coming to brushes. So brushes are used to make an electrical connection with the rotating commutator. Uh, so they supply they supply current from or to the moving commutator. So they are usually made up of carbon black and they are housed in brush holders and are in contact with the commutator surface with the help of pressure. So now coming to bearings. So bearings, ball bearings usually are used in DC machines to reduce frictional losses. So its main function is to support the machine shaft with minimum friction. So like I said, mostly ball bearings or roller bearings are used in DC machines. Now coming to the equivalent circuit of a DC machine, the first diagram you see is that of a generator and the second one is that of a motor. So E is the generated voltage, RA is the armature resistance, and VB is the brush contact voltage drop. So here, in the case of DC motor, E is the back EMF. So this is the equivalent circuit of a DC machine. Now coming to the working of a DC generator. So obviously the DC generator is based upon Faraday's law of electromagnetic induction, which of course states that when the magnetic field linked to a conductor or coil changes, and is so when the magnetic flux linked to a conductor or coil is changed, then an EMF is induced in the conductor or coil. So the magnitude of this EMF is given by, so it's called E, so it's given by minus N d phi by dt, which is the derivative of flux with respect to time. So where phi is the flux linkage of the coil and the N is the number of turns in the coil. So in case of a generator, the magnetic flux remains stationary and the coil rotates. So the EMF induced where wherever the coil rotates, the EMF is induced there. So we can say it's a dynamically induced EMF. So now let's look at each position of the coil depending upon how much EMF is induced. So in position 1, you can see the induced EMF is 0, obviously, because the movement of the coil sides is parallel to the magnetic flux. Now coming to position 2, the coil sides are moving at an angle to the magnetic flux, so hence a small EMF will be generated in the loop. Now in position 3, the coil sides are moving at right angles to the magnetic flux. So therefore the induced EMF will be the highest, like it will be maximum. So now at position 4, the coil sides are cutting the magnetic flux at an angle. So again, a reduced EMF is induced, just like in position 2. And in position 5, obviously, it's parallel again to the magnetic flux, so no EMF will be induced. And in position 6, the coil sides move under a pole of opposite polarity, and hence a polarity of induced EMF is reversed. Okay. So at position 7, again, maximum EMF will be induced. So the cycle obviously rotates with the rotation of the coil. Now we'll look at the working principle of a DC motor. So a DC motor is based on the law of electromagnetic interaction. So according to this law, whenever a current carrying conductor or coil is placed in a magnetic field, the conductor or coil experiences an electromagnetic force. So the magnetic So whenever a current carrying conductor is placed in a magnetic field, it will experience an electromagnetic force. So the magnitude of this force is given by F is equal to B into I into L, where B is the magnetic flux density and I is the current flowing in the conductor or coil, and L is the length of the conductor. So as you can see in the figure, we can understand more clearly just exactly how a DC motor works. So when the terminals of a DC motor are connected to an external source, or just like a DC supply, two things happen. So first, the field electromagnetics are excited. So N and S poles are developed. N and S poles are developed. And secondly, the armature conductors carry electric currents, where conductors under N pole carry currents in one direction, say inside the plane of the paper, while conductors under S pole carry currents in the opposite direction, say outward, or like out of out of the out of the plane of the paper. So since in this case each conductor is carrying a current and is placed in a magnetic field, due to this interaction between the current and magnetic field, a mechanical force acts on the conductor. So by applying Fleming's left hand rule, like I said earlier, the DC motor is based upon Fleming's left hand rule. So it's clear that the mechanical force on each conductor is tending to move the conductor in the opposite, I mean, in the anti-clockwise direction. So the mechanical forces on all the conductors act together to produce a driving torque that sets the armature rotating. So when the conductor moves from one pole side to another, the current in that correct conductor flows due to the commutation action, and at the same time it comes under the influence of the opposite polarity. So as a result, the direction of the force on the conductor remains the same. So in this way, the armature of a DC motor rotates continuously in one direction, therefore providing a steady output of energy. So thank you. This concludes my presentation on DC machines. I hope you all were able to understand the basics of DC machine. So thank you.